Welcome back to Science to Sleep By, where the mysteries of the cosmos unfold softly in the quiet hours of the night, and every question drifts like a star through the stillness of your mind. Tonight, we ask a question that feels almost too vast to hold. If space is expanding forever, endlessly, without pause, where is it expanding into? When we picture galaxies pulling apart, do we imagine them floating into some great emptiness? Some larger space beyond space itself? Or is the truth even stranger? You might be lying there now, in the gentle dark of your room, the hum of the world fading, your thoughts growing lighter, drifting outward like dust in sunlight. So take a slow breath, and let's travel together, beyond the edges of imagination, where science meets wonder, and questions themselves become constellations. Because the story of how the universe expands is not just about galaxies, or equations, or deep time. It's about everything. It's about what it means to exist in a universe that has no walls, no ceiling, and perhaps no end. So close your eyes. Listen to the silence between each heartbeat, and let's begin our journey through the ever-growing fabric of space, to ask the quietest, yet grandest question of all. If space expands forever, where does it expand into? Imagine the night sky stretching infinitely above you, each point of light carrying the story of a distant world. When you gaze upward, you're not just looking at stars, you're looking through time itself. Every beam of light you see began its journey long before humanity ever opened its eyes to wonder. Some of those lights started their travels when Earth was still cooling, when there were no oceans, no continents, no names for anything. Others are newer, shining from galaxies that formed billions of years after the first spark of creation. And all of them, every single one, is part of a universe that is not still, but in constant motion. It's strange to think of the universe as moving, isn't it? We tend to imagine space as an endless, silent void, cold, still, and changing. Yet, the truth is that the cosmos is alive with expansion. Space itself is stretching, the distances between galaxies growing wider and wider as the seconds pass. We might not see it happen, we might not feel the tug, but the very fabric of existence is breathing. Like the rise and fall of a cosmic chest, the universe expands, slowly and continuously, across the immensity of time. It began, as all cosmic stories do, with the Big Bang, not an explosion in space, but an expansion of space. In that first instant, there was no outside, no emptiness for the universe to burst into. Space, time, matter, and energy, all of it came into existence together, woven from the same spark. From that moment on, the universe began to stretch, to grow, to unfold itself like a vast blooming flower whose petals reach across infinity. It has never stopped. Galaxies are carried along with this flow, like leaves floating on the surface of a gently swelling ocean. They are not rushing through space as though they were projectiles shot from some celestial cannon. Instead, the space between them is increasing. The distances are stretching not because galaxies are moving, but because the stage itself is growing larger. This is the subtlety that makes the expansion of the universe so mysterious. It's not motion through space, it's motion of space. To get a sense of this, imagine dots drawn on the surface of a balloon. As the balloon inflates, the dots move apart. Each dot stays still on the rubber surface. It's the surface itself that's expanding. The balloon doesn't need to grow into anything. It simply becomes larger, and every point on its surface gets farther from every other point. Now, scale that image up beyond comprehension. Replace the balloon's surface with the fabric of space itself, and you begin to glimpse what's happening across the cosmos. When we measure the light from distant galaxies, we find that it's stretched, its wavelengths elongated as it travels through expanding space. This stretching is what astronomers call redshift light, shifting toward longer, redder wavelengths. The farther away a galaxy is, the more its light is redshifted, meaning it's moving away from us faster. This relationship, discovered by Edwin Hubble in the 1920s, was the first clear evidence that the universe is expanding. Hubble's revelation changed everything. It told us that our universe is dynamic, not static, that it had a beginning, and that it's evolving still. And yet, Even now, nearly a century later, the idea feels almost impossible to grasp. What does it mean for everything to expand? If galaxies are growing farther apart, what is it that's expanding between them? How can nothingness empty space stretch? These questions press against the limits of language itself. Because when we say space, we tend to imagine it as a background, like the black canvas behind stars. But in truth, space is not a stage at all. It is part of the performance. It's flexible, dynamic, and responsive to energy and mass. When Einstein described spacetime in his theory of general relativity, he showed that space could curve, bend, and ripple, that it could evolve. That was the moment when the universe became something more than an empty vessel. It became alive with geometry, motion, and change. Even now, as you listen, the very room around you, your bed, your city, your planet is part of this cosmic dance. The expansion is happening everywhere, at every scale. It's just imperceptibly small here, drowned out by the gravity that binds atoms, planets, and stars together. But beyond the grasp of our galaxy, where the pull of gravity weakens and space itself rules supreme, expansion reigns. Every second, millions of miles of new space come into existence between distant galaxies. The universe is not simply getting bigger in the way we think of physical objects growing. It is creating more of itself. It's almost poetic to think that while we live our small, fleeting lives, something as vast as the universe continues to swell, quietly, endlessly, with no observer to mark its rhythm. The stars we see tonight are already further away than when their light began its journey to us. Every passing moment stretches that distance a little more. The cosmos is a grand, invisible tide, rising and receding in an eternal rhythm we can only measure in billions of years. The expansion is not uniform everywhere, though. Clusters of galaxies remain bound together, held by their mutual gravity. The Milky Way and the Andromeda Galaxy, for instance, are actually drawing closer to each other, destined to merge billions of years from now. But on the largest scales, beyond clusters and superclusters, space wins. The farther out you go, the more the cosmic fabric asserts itself, pulling galaxies apart like beads sliding away on a rubber band. Astronomers often speak of the Hubble flow, the motion that arises purely from the expansion of the universe. The farther away a galaxy is, the faster it recedes. At immense distances, this speed approaches the speed of light itself. Beyond a certain point, galaxies recede so quickly that their light will never reach us, no matter how long we wait. They are already slipping beyond our horizon, leaving behind only their fading afterglow in the cosmic background. It's a sobering thought that the universe we see now is just a fraction of what exists, and that with time, even that fraction will shrink. If you could watch the universe unfold in fast motion, billions of years passing like seconds, you would see galaxies stretching apart like constellations drawn on elastic. The cosmic web, that vast network of filaments and clusters, would thin out, the spaces between its threads growing ever wider. And still, no matter how much it expands, there would be no boundary, no edge, no outer realm into which it grows. It expands within itself, forever. This is the motion that defines our existence, a motion not of things in space, but of space itself. It's an expansion so fundamental that it shapes everything we know, from the birth of stars to the silence between galaxies. It is the quiet heartbeat of the cosmos, steady and relentless. Every photon of light, every atom of matter, every whisper of gravity is carried on this vast current of creation, flowing outward from that first spark when time itself began to tick. And so, when we speak of a universe in motion, we are not speaking of chaos or speed or travel. We are speaking of a serene and unstoppable unfolding, a kind of cosmic breath that began with creation and continues still, filling every corner of existence with more of itself. The universe does not race outward into a void. It simply is, and it becomes more of what it already is with every passing moment. It stretches, it evolves, it expands not into anything, but as itself, infinitely, beautifully, quietly. When we hear the phrase, "the universe is expanding," our minds instinctively reach for something familiar, something our senses can grasp. We picture a balloon inflating, its surface stretching outward into the surrounding air. We imagine galaxies like dots drawn on that balloon, spreading apart as it swells. It's a simple image, a helpful one, but hidden within it lies a subtle misunderstanding. The balloon expands into the room around it, into space that already exists. But the universe is not a balloon in a room. There is no room outside it, no void waiting to be filled. Space itself is what's expanding. There is no into, there is only within. This idea feels unnatural because our experience of reality is shaped by boundaries. Everything we know exists somewhere. Every object sits within a space. Every movement happens towards something else. Even the air around us has direction up, down, north, south. So when we hear that space is expanding, we can't help but ask, into what? It's a question born from our earthly perspective, from living inside a world where expansion always requires an outside. But the universe operates on a level where our everyday concepts fail. Space doesn't expand into space, space expands as space. It's not filling a pre-existing emptiness. It is creating the very stage of existence as it grows. Imagine for a moment that you're standing on the surface of Earth, watching the horizon. From where you are, it looks like the world ends just beyond the curve. You can't see the other side, but you know it's there. If you could travel far enough, you'd eventually circle back to where you started. The Earth's surface doesn't need an outside for you to move around on it. It's finite but unbounded. Now imagine that concept in more dimensions. The universe could be like that. Finite, yet without an edge, expanding everywhere at once. Not into some external void, but within its own geometry. When cosmologists describe this expansion, they speak of the metric expansion of space. The word metric here refers to the mathematical way we measure distances in the universe. It's the scale itself that changes. Galaxies are not flying through space like ships on an ocean. The ocean itself is getting deeper between them. The galaxies remain nearly still, and yet their separation grows because the underlying fabric of reality stretches. This means that there is no center to the expansion. Every point in the universe sees every other point moving away. If you were standing in a distant galaxy, you would see the same pattern we see from Earth, all galaxies receding, the space between them widening. This defies intuition. We want to believe there's a center or a starting point, a direction of growth. But the expansion of the universe is not like an explosion with debris flying outward from a single origin. The Big Bang didn't happen at a point in space. It happened everywhere in space at once. In that first instant, the universe wasn't expanding into an existing void, it was creating the very dimensions in which expansion could occur. Every region of space was once compressed into that hot, dense state, and every region has been expanding ever since. When we look outward, we are not seeing space spreading into something else. We are seeing space unfolding itself everywhere equally. Think of a loaf of raisin bread baking in an oven. As the dough rises, the raisins move farther apart, not because they're crawling through the bread, but because the dough itself expands. If you were a raisin inside that loaf, you'd see other raisins receding in all directions. You might think you're at the center of the expansion, but every raisin would think the same. The bread doesn't need to expand into another space, the rising itself is the expansion. The universe behaves like that, though in dimensions beyond our perception. What makes this illusion so persistent is that we are beings who navigate by edges and directions. Our senses evolved to survive in bounded environments, not to comprehend infinity. When we imagine something growing, our minds demand an external frame of reference. We want to place the universe inside something, to picture it against some larger backdrop. But the truth is, there is no backdrop. There is no outside. The universe includes all there is, and if something existed beyond it, that too would be part of the universe by definition. The notion of expansion into something collapses because there is no external space for it to enter. Even the word expansion is misleading. It makes us think of physical motion, like air filling a balloon or ripples spreading on water. But in cosmology, expansion is not a movement through space, it's a change in space. It's the stretching of the metric, the growth of distance itself. When astronomers say that galaxies are receding, they mean that the scale of the universe's geometry is increasing. Nothing is traveling faster than light through space. It's just that the space itself between objects can increase faster than light could cross it. That's why some galaxies already lie beyond our cosmic horizon. They're not speeding away through space, but rather, the intervening space has expanded so rapidly that their light will never reach us. This expansion does not require outside any more than time requires a moment before it began. Time itself started with the Big Bang. There was no before, because before presupposes time. Similarly, there is no outside, because outside presupposes space. The universe doesn't sit within a larger void. It defines what space means. Its expansion is not an invasion of territory, it is the continuous redefinition of what distance and location are. Our language struggles to keep up with this reality. When we say, the universe expands, we're using words built for small, tangible things. The real process is something deeper, a stretching of the geometry of existence itself. If you could somehow view the universe from a vantage point outside it, though such a perspective is impossible, you wouldn't see a sphere growing into the emptiness. You would see a self-contained reality, with no edge and no beyond, where the concept of outside simply has no meaning. This is perhaps the most humbling revelation of modern cosmology. The universe needs nothing beyond itself to exist. It is self-contained, self-expanding, self-sustaining. Its growth is not a journey outward, but a deepening inward, an evolution of the very rules that define it. To ask what lies beyond the universe is to ask what lies north of the North Pole. The question dissolves because its frame of reference no longer applies. Still, it's hard not to imagine it a vast, dark sea, and the universe as a glowing bubble drifting across it. It's a poetic image, and one that has inspired centuries of thought. But science gently reminds us that the bubble is not moving through any sea. The bubble is the sea. Its edge, if there is one, is not a boundary in space, but a boundary in time. The edge of what can be known, not the edge of what exists. Everywhere you look in the night sky, the expansion is happening. Between galaxies, between clusters, between every beam of light, the emptiness itself is stretching, quietly, invisibly, without sound or direction. It doesn't need a destination. It simply continues, as it always has, as it always will, unfolding not into something new, but into more of itself. The great illusion of expansion gently dissolving into the truth of boundlessness. When Albert Einstein first introduced the concept of spacetime in the early 20th century, he redefined what it meant to exist in the universe. Before Einstein, most people, even most scientists, thought of space and time as separate, in changing backgrounds where the events of the universe played out. Space was the stage. Time was the clock ticking steadily in the background. Objects moved through space, clocks measured time, and the two never interfered with each other. But Einstein saw something deeper, something so profound that it would change the way we think about reality forever. He revealed that space and time are woven together into a single, dynamic fabric, one that can bend, stretch, twist, and ripple. In his theory of general relativity, Einstein proposed that this fabric, which we now call spacetime, is not a passive backdrop, but an active participant in the cosmos. It tells matter how to move, and matter tells it how to curve. Every planet, star, and galaxy deforms this fabric, creating the gravitational effects we feel. Gravity, in Einstein's view, is not a mysterious force pulling objects toward each other, but the natural motion of bodies following the curves and warps in spacetime itself. Imagine laying a heavy ball on a stretched rubber sheet. The sheet curves around it, and smaller marbles placed nearby roll toward the ball, not because they are pulled by an invisible force, but because the surface they rest on is curved. That is the essence of gravity in Einstein's universe. Now, extend this idea beyond a two-dimensional sheet to the four-dimensional fabric of reality, 3 dimensions of space, and 1 of time. Wherever there is mass or energy, space-time bends. The greater the mass, the deeper the curvature. That's why the Earth orbits the Sun, not because the Sun pulls it, but because the sun's immense mass warps spacetime in such a way that the Earth's straight path becomes a curved one. To us, that curved motion appears as orbiting. But in the grand geometry of the cosmos, Earth is simply following the natural contours of spacetime. This framework doesn't just explain planetary motion, it explains the expansion of the universe itself. Because if spacetime can curve and flex, it can also stretch. And that's exactly what the universe has been doing since the Big Bang. The galaxies aren't drifting apart through some empty void. They're carried by the expansion of spacetime. It's not as if space is an invisible ocean pushing galaxies outward. Instead, it's the underlying geometry of existence itself that's changing. The coordinates that define distance between galaxies are increasing because the mathematical description of spacetime's shape is evolving. Picture this. Imagine again that rubber sheet, but now instead of one heavy ball, imagine thousands of them. Stars, galaxies, clusters of galaxies all pressing down, creating valleys and curves in every direction. Now imagine that the entire sheet itself is being stretched. So the distances between all those curves grow larger over time. The objects themselves don't move across the sheet. It's the sheet that expands. This is how the universe behaves on the grandest scales. Space isn't expanding into anything. It's expanding as itself. And that expansion is not separate from gravity, not separate from time. It is part of the same fabric, the same cosmic tapestry Einstein described. Einstein's insights didn't come easily. They emerged from years of thought experiments from the mind of a man who imagined himself chasing a beam of light through the cosmos. He asked what the world would look like if you could move at the speed of light, if time itself could slow down or stretch, depending on your perspective. And through those questions, he uncovered something extraordinary, that time and space are not absolute. They are relative, flexible, and intertwined. A clock moving fast will tick slower than one at rest. A ruler moving quickly will shrink along its direction of motion. These effects are not illusions. They are real distortions of spacetime, woven into the very nature of the universe. It's difficult to imagine such distortions because we live in a world of slow speeds and weak gravity, where spacetime behaves almost flatly. But near massive objects like black holes, or across vast cosmic distances, the effects become undeniable. Light itself bends when it passes near massive stars, curving along spacetime's deformed geometry. This bending, called gravitational lensing, allows us to see distant galaxies magnified and distorted by the matter that lies between us and them. It's as if the universe itself acts as a colossal lens, warping its own light through its invisible curves. The expansion of the universe is another form of spacetime curvature, not a local warping caused by a single object, but a global stretching that affects the universe as a whole. When cosmologists describe the universe as flat, open, or closed, they're describing the large-scale geometry of spacetime. A flat universe means spacetime extends infinitely in all directions, with parallel lines never converging or diverging. A closed universe is one where spacetime bends back on itself, like the surface of a sphere, so that traveling far enough in one direction could eventually bring you back to your starting point. An open universe means spacetime curves outward, endlessly expanding without ever looping back. Each possibility is a different way for spacetime's fabric to shape reality. Einstein's equations don't just describe this geometry, they predict how it evolves. And remarkably, when applied to the universe as a whole, those equations naturally lead to expansion. They suggest that if spacetime is dynamic, if it can curve and flex, then it can also grow. When Einstein first realized this implication, he resisted it. At the time, the accepted belief was that the universe was static and eternal. To prevent his equations from predicting cosmic expansion, Einstein added a term called the cosmological constant, a kind of anti-gravity that kept the universe balanced and unmoving. But later, when Edwin Hubble discovered that galaxies are indeed receding from each other, Einstein reportedly called the cosmological constant his greatest blunder. Ironically, modern cosmology would find that this constant, or something very much like it, does exist. It's what we now call dark energy. the mysterious force driving the accelerated expansion of the universe. Einstein's spacetime gave us a language for understanding not just where we are, but what we are. It told us that everything in existence, matter, energy, gravity, if in time, is connected through geometry. There is no separation between the arena and the action. The arena itself is alive. When space expands, when time flows, when gravity bends light, these are not separate events but expressions of the same fabric, shifting, breathing, evolving. The entire cosmos, from the smallest particle to the largest galaxy cluster, is woven into this continuous field. And within that fabric, everything moves not through emptiness, but through curvature. Every second that passes, the shape of the universe changes slightly. Every photon of light that travels across billions of years does so along the contours of this invisible structure, its path bent by every star, every galaxy, every ripple of spacetime it encounters. When we observe the cosmic microwave background, the faint afterglow of the Big Bang, we are seeing the stretched, cooled radiation imprinted on spacetime itself. Its faint variations are like wrinkles in the cosmic fabric, tiny differences that grew into galaxies, stars, and planets into us. Spacetime is not something that exists apart from us. It's the medium through which we exist at all. Every heartbeat, every second of thought, every breath of air, all happen within its flow. When we move, we are tracing paths through spacetime. When we rest, we are suspended within it. Our lives are threads in this immense cosmic fabric, woven by the same physics that guides galaxies. It's an idea so vast and yet so intimate that it's difficult to comprehend. Einstein's vision transformed the question of expansion into something deeper. Space is not expanding into an outside realm, because there is no outside of spacetime. The fabric itself has no boundary. It defines all that can be. Its expansion is not the stretching of something contained, but the evolution of the container itself. It is not growth through space, it is growth of space. The fabric of spacetime is both the canvas and the painting, the rhythm and the melody, the silent geometry through which all of existence unfolds. To understand what it truly means when scientists say that the universe is expanding, we have to look closer at one of the most misunderstood yet fascinating ideas in all of cosmology, the concept of the metric expansion of space. This phrase might sound mathematical, but it describes one of the most profound realities of existence. It tells us that the universe isn't simply filled with galaxies moving through space like ships across an ocean. Rather, the very ocean itself is growing. The distances between galaxies are increasing, not because they are flying away from one another through space, but because the metric, the way space itself measures distance, is stretching over time. To grasp this, we must first understand what physicists mean by metric. In geometry and physics, a metric is a way of defining how distances are measured between 2 points. On Earth, for instance, we use a relatively simple metric because space here behaves in an almost flat, Euclidean way. The distance between 2 cities can be measured directly, and the rules of geometry are consistent everywhere. But in Einstein's universe, the one governed by spacetime, distances are not so simple. Space can curve, time can stretch, and the metric can change depending on the mass, energy, and shape of the universe itself. The metric is like the ruler of reality, but it's a ruler that changes its length as the universe evolves. When cosmologists say the universe is expanding, what they mean is that this cosmic ruler, the metric, is increasing in scale. If you were to place 2 galaxies far apart from each other and wait billions of years, the number of miles or light years between them would grow. Even if both galaxies were perfectly still relative to the expanding space around them, the galaxies themselves aren't moving through space. They are carried along with the expansion. It's like dots drawn on the surface of an inflating balloon. The dots do not move on their own, but as the balloon stretches, the space between them increases. The balloon's surface is not expanding into anything else. It's the 2-dimensional representation of the universe's expanding metric. What's extraordinary is that this metric expansion doesn't happen everywhere in the same way. On small scales, within galaxies, solar systems, and even clusters of galaxies, gravity dominates. The gravitational pull between stars and planets holds them together against the universe's expansion. The space between the Earth and the Sun, for example, is not stretching. It's tightly bound by gravity. It's only on cosmic scales, across the immense gulfs between galaxies, that the expansion becomes apparent. It is there, in the dark reaches between galactic clusters, that space quietly, steadily grows. This process was first discovered through observation. When Edwin Hubble examined the light from distant galaxies in the 1920s, he noticed something peculiar. Their light was redshifted, meaning its wavelengths were stretched toward the red end of the spectrum. The farther away a galaxy was, the more its light was stretched. Hubble realized that this stretching wasn't caused by motion through space, but by the expansion of space itself. The wavelengths of light traveling through that expanding space were literally stretched along with it. The deeper we look into the cosmos, the more stretched that light becomes, and the faster the galaxies appear to recede from us. This linear relationship between distance and redshift became known as Hubble's law, and it remains one of the cornerstones of cosmology. Yet, this discovery carried an unsettling implication. If the universe is expanding now, it must have been smaller in the past. Tracing the expansion backward in time leads us to a moment when everything space, time, matter, and energy was compressed into an unimaginably dense state. This is the Big Bang, not an explosion in space, but the beginning of expansion of space. It's crucial to remember that there was no outside into which the universe expanded. The Big Bang happened everywhere at once, and space itself has been growing ever since. Every region of the cosmos was once closer to every other region, and every point in space is part of this continuous stretching. As the universe expands, it carries profound consequences for the way we understand its evolution. When space expands, it affects not only distances, but also the density of matter and radiation. As the scale of the universe increases, the energy of photons, the particles of light, decreases, leading to the cooling of the cosmos. This is why the universe today is much colder than it was billions of years ago. The faint afterglow of the Big Bang, known as the cosmic microwave background, is a perfect relic of this cooling process. When it was first released, the universe was filled with blinding radiation, thousands of degrees hot. Over billions of years, as the universe expanded, the wavelengths of that radiation stretched into the microwave range, cooling to just a few degrees above absolute zero. This stretching of light in space is not like anything we experience in our daily lives. On Earth, expansion means something moves outward into an empty region, like air filling a balloon. But cosmic expansion has no such outside. It is a scaling of the geometry itself. The coordinates of space remain the same, but the distance between them grows. Every galaxy in the universe sees itself as being at the center of this expansion, because from every vantage point, the pattern looks the same: galaxies receding in all directions. This universality is one of the most elegant features of the cosmos. There is no privileged location, no center, no edge. Expansion happens everywhere at once. As astronomers refined their measurements, they discovered something even more astonishing. The expansion of the universe isn't slowing down, as one might expect from the gravitational attraction of all its matter. Instead, it's accelerating. Distant galaxies are not just moving away, they're moving away faster and faster over time. This revelation came from observing distant supernova in the late 1990s, and it led to the discovery of a mysterious force called dark energy. This invisible energy seems to make up roughly 70% of the universe, acting as a kind of cosmic pressure that drives the acceleration of expansion. No one knows exactly what dark energy is. It may be related to Einstein's cosmological constant, a term he once added and later rejected, or it may be something entirely new. But whatever its nature, it shapes the metric of space on the grandest scales, dictating how the universe evolves. If we could visualize this metric expansion, it would appear as a continuous stretching of the cosmic web, that vast structure of filaments and voids that make up the large-scale universe. Galaxies are like luminous beads strung along threads of dark matter, and as the universe expands, the threads elongate. The cosmic voids between them grow larger, swallowing light and time. Galaxies within those filaments remain gravitationally bound, but the gaps between structures widen. Over billions of years, entire clusters of galaxies will slip beyond our cosmic horizon, disappearing from view forever as the metric expansion carries them away faster than their light can travel back to us. This idea is not just scientific, it's deeply philosophical. The metric expansion of space challenges the way we think about motion, distance, and the nature of change. It tells us that the universe doesn't need something external to push against or grow into. It expands because the mathematical rules that define its structure evolve with time. Every new moment brings more space, more distance, more room for existence to unfold. The expansion is built into the very equations that describe reality. Even now, as you sit beneath the same stars that ancient humans once looked upon, the space between those stars is changing. The light from them stretches a little more each second. The galaxies that form the tapestry of the night sky are not stationary, they're part of a grand cosmic rhythm, drifting apart as the universe breathes in its silent, eternal way. We don't feel it, we don't see it, but with every heartbeat, the metric of the cosmos grows ever so slightly larger. The universe doesn't expand into emptiness. It generates more of itself, reshaping the definition of distance, of location, of time, in an endless act of creation that began long before we were here to notice it. When we look up into the night sky, we are not seeing the universe as it is now, but as it once was. Every glimmering point of light that reaches our eyes has traveled across vast distances of space and even greater spans of time. The light from the moon is just over 1 second old. The light from the sun is 8 minutes old. The light from the nearest star, Proxima Centauri, began its journey more than 4 years ago. And when we gaze at the faintest, most distant galaxies through powerful telescopes, we are looking billions of years into the past, to a universe that was younger, smaller, and hotter than the one we live in today. This is one of the most profound aspects of cosmic exploration. To look farther is to look deeper into time itself. But no matter how powerful our instruments become, there is a limit to what we can see, a boundary not of physical walls, but of light and time. This boundary is called the cosmic horizon, the edge of the observable universe. The observable universe is the portion of the cosmos from which light has had time to reach us since the Big Bang. Beyond this horizon lies more universe, perhaps infinite, but we can never see it, because its light has not yet had enough time to travel across the expanding space to reach us. In a sense, we are surrounded by a cosmic fog, not made of gas or dust, but of time itself. The horizon defines the maximum distance we can observe, not because there is anything physically blocking our view, but because the speed of light and the age of the universe together impose a fundamental limit. To understand this horizon, we must remember that the universe has a finite age, about 13.8 billion years. That might make it tempting to assume that we can only see objects up to 13.8 billion light-years away, since light travels 1 light-year per year. But the reality is stranger. Because space itself has expanded during the time that light has been traveling, the galaxies that emitted the light we see today are now much farther away than they were when that light began its journey. In fact, the current radius of the observable universe is roughly 46 billion light-years. That means we can observe light that has been traveling toward us for 13.8 billion years. But the galaxies that emitted it are now 46 billion light-years distant due to the ongoing expansion of space. The horizon, therefore, is not a static distance. It's a constantly moving frontier shaped by the growth of the universe itself. Beyond that horizon lies a region of the cosmos we can never know, because its light will never reach us. The expansion of space stretches the distance between us and those regions faster than light can cross it. It's not that light is too slow, but that the space it must traverse is growing faster than light can bridge. Those parts of the universe recede from us, not because they move through space at superluminal speeds, but because the very metric of space carries them away. This creates a profound asymmetry between what exists and what can be known. The universe might be infinite, but our view of it is forever finite. When astronomers map the observable universe, they see something extraordinary. Galaxies form a vast, intricate network, a cosmic web made of filaments and clusters separated by enormous voids. These structures stretch for hundreds of millions of light years, shaping the large-scale architecture of everything we can see. Yet, beyond this visible web, there is more. Perhaps an endless continuation of the same structure, or perhaps something completely different, forever hidden beyond our cosmic horizon. We live inside a cosmic bubble of knowledge, a sphere of visibility bounded not by matter, but by time's finite reach. Even within this bubble, there are horizons of different kinds. One is called the particle horizon, which marks the limit of how far we can currently observe. Another, even more mysterious, is the event horizon of the universe, the limit beyond which we will never be able to see, no matter how long we wait. Because the universe's expansion is accelerating, distant galaxies are being carried away from us faster and faster. This means that even light emitted now from some galaxies will never reach us in the future. Over time, more and more galaxies will cross that event horizon and vanish from our cosmic awareness. Not because they cease to exist, but because the space between us grows too rapidly for their light to overcome. This leads to a haunting realization. The universe we can see is shrinking, not in size, but in content. As billions of years pass, the accelerating expansion will carry distant galaxies beyond our reach. Future astronomers, living perhaps trillions of years from now, will see only the faint light of a few nearby galaxies. The vast cosmic web that we see today, the evidence of an expanding universe, the key to understanding the Big Bang, will fade from view entirely. The night sky will become emptier, quieter, lonelier. In that far future, even the microwave background radiation, the faint afterglow of creation, will stretch beyond detectability, its wavelengths expanding into oblivion. The universe will appear static once more, though only because its expansion has carried away all traces of its own history. Yet, in our moment, the observable universe still reveals its secrets. With telescopes like Hubble and the James Webb Space Telescope, we can see galaxies that formed when the universe was less than 1 billion years old. We can observe the birthplaces of stars and the faint cosmic light that has traveled across unimaginable distances to reach us. Each photon that enters our instruments carries with it a message from the past, a record of conditions billions of years gone. The more we look, the further we peer into the universe's memory. The cosmic microwave background, first detected in 1965, is the oldest light we can ever observe. It was released when the universe was just 380,000 years old, when atoms first formed and the cosmos became transparent to radiation. Before that moment, the universe was a dense, hot plasma. Light couldn't travel freely because it was constantly scattered by charged particles. When the universe cooled enough for hydrogen atoms to form, light broke free and began its journey across expanding space. That light still surrounds us today, stretched into microwaves by billions of years of expansion. It's not visible to the eye, but it fills every corner of the sky, a whisper from the dawn of time. When we map that radiation, we see faint variations in temperature, tiny differences in the density of matter in the early universe. Those minute fluctuations, no larger than 1 part in 100,000, became the seeds of all future structure, the galaxies, stars, and planets we know today. The cosmic microwave background is more than just ancient light. It's a fossil of spacetime itself, a picture of the universe before it had form or complexity. It's the ultimate horizon, the deepest we can ever see into the past. Standing here on Earth, on this small blue world orbiting an ordinary star, we are observers at the center of our own visible sphere. Not because we occupy a special place in the cosmos, but because every observer, no matter where they are, has their own observable universe, their own horizon defined by the same rules of light and time. If there are beings on a distant planet in another galaxy, they too would see themselves at the center of a sphere of light 46 billion light-years in radius. Their horizon would overlap with ours in some regions and diverge in others. The universe has no single center, yet every point is a center of observation. every conscious being a witness to a different portion of the same grand whole. The cosmic horizon is both a scientific boundary and a philosophical one. It marks the edge of what we can know, and by doing so, it defines the limits of our understanding. It reminds us that knowledge itself is bounded by the structure of reality, by the finite speed of light, the age of the universe, and the ceaseless expansion of space. We can model what lies beyond, imagine it mathematically, infer its properties from what we can see, but we will never touch it. The light from those unreachable regions will forever remain just out of reach, their stories untold, their existence known only through the silence that follows the edge of observation. In that silence, there is something profoundly human, the mixture of awe and humility that comes from knowing that our universe is vast beyond comprehension, yet finite in what we can perceive. The cosmic horizon isn't a wall but a mirror, reflecting back the limits of perception itself. It reminds us that the universe is not just a physical space, but a temporal one, that to see farther is to look backward, and that the light we receive is the voice of time speaking across the ages. Every star, every galaxy, every flicker of radiation that reaches us is a message from a part of the cosmos that still exists, but has already drifted beyond our sight. The horizon stands as the quiet, glowing boundary between the knowable and the eternal unknown. When we talk about the expansion of the universe, we inevitably come to a haunting and fundamental question: does the universe go on forever? Or does it have an edge, a boundary beyond which there is nothing? This question has echoed through human history, from the ancient philosophers who imagined crystal spheres surrounding the Earth, to modern cosmologists who probe the very fabric of spacetime with equations and telescopes. It is a question that challenges our intuition, because in our everyday experience, everything has limits. Every room has walls. Every planet has a surface. Every object has edges. Yet the universe, the totality of everything that exists, seems to defy that simple logic. If space itself is expanding, where does it expand into? If the cosmos has no edge, how can it be finite? If it is infinite, how can something boundless continue to grow? These paradoxes sit at the heart of Keynote 6, where we explore the nature of the universe beyond the horizon, the question of whether it is infinite or finite. To begin unraveling this, we must turn to the geometry of the cosmos. Einstein's theory of general relativity tells us that space is not merely an empty stage on which matter and energy move. Space itself is dynamic, shaped and curved by the very matter and energy it contains. The geometry of the universe, its curvature, determines whether it is open, closed, or flat. A closed universe would be finite, like the surface of a sphere, curving back on itself. If you could travel far enough in one direction in a closed universe, you would eventually return to your starting point, not because you crossed a boundary, but because space itself wraps around. A flat universe, on the other hand, extends infinitely in all directions, with no curvature on large scales. It is boundless, like an endless plane. An open universe has negative curvature, like a saddle, stretching infinitely, but expanding forever faster. Which of these descriptions matches our reality depends on how much matter and energy the universe contains. For decades, scientists have tried to measure this cosmic curvature with ever greater precision. Observations of the cosmic microwave background, the ancient radiation left over from the Big Bang, have provided the clearest answers. By analyzing patterns in that light, cosmologists can determine the overall geometry of space. The results, especially from missions like WMUP and Planck, have shown that the universe appears astonishingly flat, with a margin of error so small that if it is curved, the curvature must be extremely slight. This implies that on the largest scales we can observe, the universe behaves as if it is infinite. However, flat does not automatically mean infinite. It only tells us that if the universe is finite, its size is so vast that we cannot detect its curvature within our observable horizon. Imagine standing on the surface of the Earth. From your perspective, the ground appears flat, even though you know the planet is round. The curvature of the Earth is imperceptible over short distances, because you are too small compared to the planet's scale. In the same way, our observable universe might be just a tiny region of a much larger cosmic structure that curves in a way we cannot yet perceive. The universe could be finite and unbounded, looping back on itself, or it could be truly infinite, stretching beyond all conceivable limits. If the universe is finite, yet unbounded, that means it has no edge, no boundary, and no outside. Space curves back onto itself like the surface of a higher dimensional sphere, what mathematicians call a three-sphere. You could, in principle, travel in a straight line forever, and eventually return to where you began, just as a traveler sailing across the Earth eventually comes back to the same spot. In such a universe, the expansion of space doesn't push outward into emptiness. It simply scales the internal distances of this self-contained structure. Every part of space expands relative to every other part, but there is no beyond into which it grows. If, on the other hand, the universe is infinite, then the expansion is even more mind-bending. In an infinite universe, space itself has no end, and yet it still stretches. The distance between galaxies increases, but there is no boundary being pushed outward. Instead, every region of space expands uniformly. The universe can be infinite in size and still grow, because expansion doesn't mean adding new space at the edge, it means increasing the scale of space everywhere at once. It's not the size of the universe that changes, but the scale of its geometry. In an infinite universe, expansion is not about creating new territory, but about redefining distances across all of existence simultaneously. This concept challenges the human mind, which evolved to deal with finite spaces. When we picture expansion, we think of an object swelling within an external medium, a balloon inflating in air, a ripple spreading across water. But the universe doesn't expand into anything because there is no external space beyond it. Space itself is all there is. The notion of outside simply has no meaning in cosmological terms. Asking what lies beyond the universe is like asking what's north of the North Pole. The question itself doesn't fit the geometry of reality. One way to visualize this is through analogy. Imagine a two-dimensional being living on the surface of a balloon. To that being, the balloon's surface represents the entire universe. As the balloon inflates, every point on the surface moves away from every other point. The being perceives expansion, but cannot conceive of the third dimension in which the balloon exists. From its perspective, there is no inside or outside, only the surface. Likewise, we live within a three-dimensional space that may be curved or flat in higher dimensions, but we can only perceive the expansion internally. We cannot step outside the universe to see it grow. The question of finiteness or infinity also ties deeply into the idea of the multiverse. Some cosmological theories suggest that our universe may be just one bubble in a vast cosmic foam, each bubble representing a separate universe with its own laws of physics, expanding within a higher dimensional reality. In that scenario, our universe's expansion could be part of a larger, eternal process, a cosmic sea of universes constantly inflating, colliding, and budding off new regions of spacetime. This perspective redefines the word universe itself, transforming it from the totality of existence to merely one domain within a boundless multiversal expanse. The inflationary theory of the early universe gives further weight to this idea. Shortly after the Big Bang, the universe underwent an unimaginably rapid period of exponential expansion, driven by a high-energy vacuum state. This inflation smoothed and flattened the cosmos, explaining why it appears so uniform today. However, some models of inflation predict that this process never completely ends. While inflation stops in our region, it continues elsewhere, creating an infinite mosaic of universes. If this is true, then the observable universe is just a small pocket of a much greater reality, a single expanding bubble in a sea of eternally inflating space. But even without invoking the multiverse, the question of infinity versus finiteness carries profound implications for our understanding of existence. If the universe is finite, it might someday curve back on itself, perhaps leading to a big crunch, where expansion reverses and all matter collapses inward again. If it is infinite and expansion continues forever, then the cosmos will face an opposite fate, a heat death, where galaxies drift apart, stars burn out, and entropy reaches its maximum. In that distant future, space would be cold, dark, and nearly empty, with only the faint radiation of decayed matter lingering in the void. Expansion would continue endlessly, but meaninglessly, as everything becomes evenly spread across infinite space. The idea of infinity itself is both alluring and unsettling. In mathematics, infinity is not a number, but a concept, something that cannot be measured, counted, or contained. When applied to the universe, it implies that there are infinite galaxies, infinite stars, and perhaps infinite versions of ourselves scattered across the cosmic landscape. Somewhere in an infinite expanse, there could exist regions identical to our own observable universe, differing only in minute details. The infinite universe implies infinite possibility, but also infinite repetition. It challenges the uniqueness of our existence and the very definition of reality. Whether finite or infinite, the universe has no edge in the conventional sense. There is no wall, no boundary, no outer surface marking the end of space. The cosmos does not sit inside a larger void, nor does it expand into emptiness. Space itself is the framework of existence, and it defines what inside and outside even mean. Beyond that framework, those concepts dissolve. To say that the universe expands is to say that the distances between points of space grow larger, not that it occupies more territory. It's not an explosion, but a stretching of geometry, scaling of existence itself. This realization forces us to redefine what we mean by where. When we ask, where does the universe expand into? We are unknowingly assuming that space exists outside the universe. But space, by definition, is what the universe is made of. There is no beyond, because there is nothing outside the structure of spacetime. Space doesn't need a container any more than time needs a direction outside itself. The universe is self-contained, whether infinite or finite. It encompasses all that can exist. In the end, the debate between a finite and infinite universe remains open, shaped by both observation and theory. Our instruments can only probe so far, and our mathematics can only describe so much. What lies beyond our cosmic horizon may forever remain hidden, a mystery folded into the fabric of existence itself. What we do know is that the universe continues to expand. Not into something, but of itself, carrying with it the endless question of whether infinity is a destination or the eternal nature of reality itself. When we talk about the expansion of the universe, we are not just describing a current event, but also peering into its destiny. The fate of the cosmos is written into the rhythm of its expansion, a slow, steady breathing of spacetime that began with the Big Bang and continues into a future that stretches beyond imagination. If space expands forever, as current evidence suggests, then the universe is on a trajectory toward a lonely, cold, and ever-diluting existence. Yet within that distant fate lies a story that blends cosmic physics with existential wonder, a story of what it means to live in a universe that will never stop growing, never stop changing, and never truly end. The first clue to the universe's future lies in its past. When the Big Bang occurred about 13.8 billion years ago, the universe was unimaginably dense and hot. It expanded rapidly, cooled, and allowed matter to form. Gravity then pulled matter into clumps, forming galaxies, stars, and planets, the cosmic architecture we see today. For much of its history, the expansion was slowing down because of gravity. Every particle of matter pulled on every other particle, trying to resist the outward rush. For decades, scientists assumed that gravity would eventually win, halting the expansion and perhaps reversing it into a catastrophic collapse known as the Big Crunch. But in the late 1990s, something astonishing was discovered. The universe's expansion wasn't slowing down, it was accelerating. This acceleration is driven by a mysterious force called dark energy, which seems to act as a repulsive pressure inherent in the fabric of space itself. Unlike matter and radiation, which dilute as the universe expands, dark energy appears to remain constant, meaning that as more space comes into being, more dark energy is created. This discovery changed everything about how we think the universe will end. If dark energy continues to dominate, the expansion will never cease. The cosmos will continue to grow faster and faster, galaxies drifting apart at increasing speeds until even light cannot bridge the gulf between them. To understand this fate, it helps to imagine the large-scale structure of the universe as a cosmic web, a network of filaments composed of galaxies and dark matter, stretching across billions of light years. Right now, this web still holds together through gravity. Clusters of galaxies remain bound, and the Milky Way is part of one such cluster known as the local group. But over cosmic timescales, the relentless expansion will change this balance. In a few tens of billions of years, distant galaxies outside our local group will slip beyond our cosmic horizon. Their light will be stretched so much by expansion that it will no longer reach us. From our perspective, they will simply fade away, disappearing into the darkness as if the universe itself were turning off its stars, one by one. As time progresses, only the galaxies that are gravitationally bound to us, the Milky Way, Andromeda, and a few smaller neighbors, will remain visible. Eventually, even those will merge into a single massive elliptical galaxy. Beyond it, the sky will be black. The cosmic web will unravel, not because the galaxies themselves move, but because the space between them grows faster than any signal can travel. The observable universe will shrink, not in size, but in content, as everything beyond our gravitational island vanishes over the horizon. The physics of this distant future can be traced through several stages. In the next 100 billion years, star formation will slow dramatically. The supply of interstellar gas, which fuels the birth of new stars, will be used up or expelled by supernova and galactic winds. The universe will enter an age of aging stars, long-lived red dwarfs burning dimly, illuminating sparse pockets of the cosmic night. Over trillions of years, even these faint stars will exhaust their fuel, becoming white dwarfs, neutron stars, or black holes. The night sky will darken further, and the temperature of space will continue to drop, as the cosmic microwave background stretches into wavelengths too long to detect. This gradual fading leads to what scientists call the degenerate era. During this time, the universe will be populated mostly by stellar remnants, white dwarfs slowly cooling into black dwarfs, dense spheres of carbon and oxygen no longer emitting light. Black holes will still punctuate the darkness, swallowing the occasional wandering object, but even they will not last forever. According to Stephen Hawking's theory of black hole evaporation, black holes emit a faint radiation and lose mass over time. For the largest black holes, this process takes an almost unimaginable span, 10,100 years or more. But eventually, they too will evaporate, releasing their energy as the last flickers of light in an ever-darkening cosmos. If dark energy remains constant, the expansion will continue exponentially. The distances between all unbound objects will increase faster and faster. Galaxies will vanish from sight, stars will fade, and even atoms may not remain safe forever. Some cosmological models predict a scenario known as the Big Rip. In this hypothetical future, the repulsive force of dark energy grows stronger over time, tearing apart galaxies, then solar systems, then planets, and eventually in atoms themselves. Space would expand so violently that the very fabric of matter would unravel, leaving only a diffuse mist of energy scattered through infinite emptiness. However, the Big Rip depends on the precise nature of dark energy, which remains one of the greatest mysteries in modern science. If dark energy is constant, a cosmological constant, as Einstein once proposed, then the expansion will continue forever at a steady exponential rate. Galaxies will drift away, but atoms will remain intact. The universe will approach a state of heat death, also known as the Big Freeze. In this scenario, as expansion continues, all available energy becomes evenly distributed. No gradients of temperature or density remain to drive motion or life. Entropy, the measure of disorder, reaches its maximum, and the universe settles into an eternal stillness. As we drift to the end of this journey through cosmic time, The question that began it all still lingers softly in the air. If space expands forever, where does it expand into? We have traveled from the first trembling moments of the universe to the distant horizons of what may come, tracing the invisible threads of reality as they stretch beyond imagination. Along the way, we discovered that space does not expand into something else. It expands within itself. The universe is not a balloon rising into a void, but a self-contained fabric, unbounded and complete. It is a reality that grows without edge, a vastness that carries everything within it, including us. We have seen how galaxies drift apart, not because they are flying through space, but because the space between them grows. We have watched time slow and stretch as the universe expands, felt the quiet pull of dark energy as it drives everything outward, and glimpsed the distant future when the stars will fade, and the cosmos will cool into stillness. The expansion of space is not only a scientific truth, but a profound meditation on existence itself. It tells us that change is not a flaw in the universe, but its essence. That to be alive, to exist, to think, is to expand. In the endless unfolding of the cosmos, we are but a brief whisper, and yet within that whisper lies awareness. We are the universe made conscious, reflecting upon its own immensity. Every observation, every thought, every question about the stars is part of the same expansion, growth not of matter but of understanding. The universe expands outward. The human spirit expands inward, reaching for meaning in the silence between galaxies. Perhaps that is what makes this cosmic truth so beautiful. The expansion of the universe mirrors the expansion of our minds. Just as space has no boundary, neither does curiosity. Just as the galaxies recede into the infinite, so do our thoughts stretch toward the unknown. We do not stand outside the universe, watching it grow. We are growing with it, carried within its breath, part of its eternal motion. And as you lie here now, breathing softly beneath the quiet ceiling of night, remember that every inhale mirrors the rhythm of creation. The air you draw in has drifted across centuries, through the atoms of stars, through the long history of expansion itself. You are made of the same universe you wonder about, built from its particles, shaped by its forces, sustained by its light. The universe expands forever, not into something else, but into itself, into possibility, into memory, into being. And within that infinite unfolding, your awareness, your thoughts, your very existence are part of its story. The cosmos is not out there. It is here, within you, expanding still in silence and wonder and endless becoming.